Welcome to our video lecture on climate change. Our essential understanding for today: concentrations of gases in the atmosphere have significant effects on climates experienced at Earth's surface. Our objectives: we're going to explain the greenhouse effect, we're going to review the electromagnetic spectrum, we're going to compare and contrast the properties of methane and water, we're going to discuss evidence that CO2 levels are rising, then we're going to wrap up with a little distinction between climate change and ozone depletion, both important challenges that we are facing, but slightly different. So we're going to look here first at greenhouse effect. We have these gases, greenhouse gases, carbon dioxide and water vapor are very significant in terms of keeping the planet warm. We've got other ones, methane and nitrogen oxides are also greenhouse gases, but they don't have as big an impact as CO2 and water vapor. Our greenhouse gases make up less than 1% of the whole entire atmosphere, but they do have a big impact on us because of their ability to absorb long-wave radiation. So that's basically what happens in greenhouses. Here's an example of a greenhouse. So sunlight is going to pass through the glass. It's going to hit things inside the greenhouse. This radiation from the sun is going to be converted into heat. We're going to warm up these plants. The heat is going to be reflected, but some of it gets caught in the glass. The glass can re-emit that heat. And so we can warm up this greenhouse because the sunlight radiation is converted into heat radiation and then just kind of gets trapped inside. This is what also happens in our atmosphere with those greenhouse gases. So since we're talking about these radiation things coming from the sun and getting re-emitted as heat, it's worth a quick review of the electromagnetic spectrum. We learned about this back in physics, but here is a quick look. So visible light is in here. So this is the light that is visible, hence visible light. Slightly less energetic than visible light is infrared, also known as IR. Slightly more energetic than visible light is ultraviolet, also known as UV. The reason that these guys have different energies is because of their waves. So light travels, according to physicists, as both particles and in waves. And so we're going to review waves super quick. So waves have wavelengths. And so from here to here, from a corresponding point to the next corresponding point on the waves, this is known as the wavelength. And here we have longer wavelengths. Long wavelengths are a little bit less energetic. So longer wavelengths, a little bit less energetic. Over here, notice that we are getting shorter and shorter and shorter wavelengths. These guys are much more energetic. So these short wavelengths are going to have higher amounts of energy. They're more energetic. So infrared is slightly less energetic and has a longer wavelength. UV radiation has higher energy and has a shorter wavelength. So when we're talking about long wave and short wave, infrared is long wave, UV is short wave. Good. So what happens is this. That short wave, notice that the wavelengths here are a little bit short. That short wave radiation, that UV radiation coming from the sun, some of it is going to get to Earth's surface. It's then re-radiated from the surface as infrared, longer wave radiation. So short wave radiation comes from the sun. That short wave UV radiation is going to, some of it is going to hit the Earth's surface and it's going to get warmed up. The Earth's surface is going to get warmed. That longer wavelength infrared radiation is going to be refracted off of the surface of the Earth. Some of it is going to pass through the atmosphere and out into space, but some of it is absorbed and re-radiated by these greenhouse gas molecules. And so the greenhouse gases will keep this infrared, long wave infrared radiation trapped in the atmosphere of the Earth, and it keeps that Earth warm, which is good. This is natural and good. If we didn't have the greenhouse effect happening at all, we would be very, very, very cold, a little bit frozen here on Earth. There would not be a whole lot of life happening. The challenge is that our greenhouse gases are increasing, which is increasing that heat that is being trapped in the atmosphere, and that's going to lead to some problems. So quick look at our main greenhouse gases. Most of it is CO2, carbon dioxide. It is produced by the burning of fossil fuels to make electricity, the burning of fossil fuels when we drive our cars. In industry, they're going to be making lots of things, cement and steel and iron, lots of CO2. So the great majority of our greenhouse gas problems are coming from carbon dioxide. So we talk about methane. Methane is another example of a greenhouse gas. And we like to talk about how methane and water, even though they have similar molar masses, are quite different. So methane has a molar mass of 16 grams per mole. Water has a molar mass of just about 18 grams per mole. This is super similar, and so we should think that water and methane act pretty similarly, but they definitely do not. So water is polar. The reason that it is polar is because oxygen has these non-bonding pairs of electrons, and oxygen is also more electronegative than is hydrogen. And so the electrons that are being shared here in these bonds between oxygen and hydrogen are closer to the oxygen. So these two things combine to make the oxygen side of water partially negative. We use that lowercase delta, partially negative, on the oxygen side, which leaves the hydrogen, since the electrons are not near it, to be partially positive. So we have a positive pole and a negative pole, which means that the next water molecule that comes, these hydrogens that are partially positive are attracted to the oxygen that is partially negative, and they stick together like little magnets. So water is polar. Methane is non-polar. Methane is non-polar. There is some electronegativity differences. Carbon's a little bit more electronegative than is hydrogen. But because the whole outside of the molecule is symmetrical, we have a non-polar methane. So water is going to have hydrogen bonding because of those poles. Methane does not. Its only force of attraction, we call it London dispersion, which is significantly weaker in methane than the hydrogen bonding is in water. The boiling point of water is 100 degrees Celsius. We need to add a lot of heat to get water to go from a liquid to a gas. If I want to turn methane into a liquid, I need to get it down to negative 162 Celsius. So this is the boiling point of methane, the boiling point of water. Heat of vaporization, remember this is the amount of energy needed to turn water from a liquid into a gas. Heat of vaporization for water is 2,260 joules of energy per gram of water. For methane, I need only 760 joules per gram. So not as much energy needed to vaporize methane, which is why water is a good coolant and methane is not. And then also specific heat. Remember that specific heat is the amount of energy required to change the temperature of 1 gram of the substance by 1 degree Celsius. In water, that is 4.18 joules per gram degree Celsius. In methane, we need just about half of that, so only 2.2 joules per gram degree Celsius. So definitely very different properties despite the fact that their molar masses are so similar. There are correlations between global temperatures and carbon dioxide concentrations on Earth. So back to climate change, back to carbon dioxide. We see in these graphs that Earth's temperature is changing quite a bit. So this is average over the last 140 years across the globe, and we can see that very recently, just in the last 20 years here, we've had a significant increase in global temperatures. This is just looking at northern hemisphere over the past 1,000 years. This is our data that we actually are able to collect. This is proxy data, which means that we had to use data from things like ice that we dug out of the poles to try to figure out what the temperatures were over the past. And we can again see that very recently we have a bigger increase compared to the average. So here we're looking at not just temperatures, but temperatures with carbon dioxide levels. Yes, Earth's temperature and CO2 levels have always cycled. The challenge is now we're just increasing at a much faster rate. than we have seen historically, which concerns us because we know that more CO2, more greenhouse gases means more increases, a faster rate of increase of temperatures on the globe. So here we're looking at amounts of northern hemisphere sea ice, so looking at the poles, and certainly there are going to be differences, right, amongst the seasons, but notice that 1910 versus 2005 were quite a bit lower through all the seasons. So we've definitely had some decreases across the board. We can see images of Arctic sea ice. Notice 1879, 1995, 2012. The amount of ice on the at the North Pole is significantly less now than it was only in 1995, significantly less than it was back in 1879. So these are all problems. These are some of the consequences of climate change, greenhouse effect. We are warming up the Earth at a faster rate than we have before. This is going to lead to those polar ice caps are melting. This is going to lead to higher sea levels. The less ice, the more water we have in the oceans. Sea levels are going to rise. We're going to lose coastal lands. We are worried about habitats shifting. So where polar bears live now is not a good habitat for polar bears anymore. Where are they going to go? We're also concerned about crops. So in the United States, we have this lovely section of the country where we grow wheat really well, where we grow corn really well. We're worried about, as things warm up, as weather shifts, as weather gets more extreme, these agricultural belts might shift. Canada might become the place to grow wheat very well. It might be too warm here in the United States because we're too close to the equator as things get warmer. So that's greenhouse effect. I'm going to have us think about how ozone depletion is different, also important, but a little bit different. So we have these things called CFCs, chlorofluorocarbons. These chlorofluorocarbons are released by refrigerants and aerosol molecules. The CFCs attack the ozone that's in the upper pieces of the atmosphere. Ozone here at the surface of the Earth is bad. It is it's a pollutant. It can trigger asthma attacks, but up in the very tippy top of the atmosphere, it's really good. It actually blocks some of that UV radiation coming from the sun. Because we were making too many CFCs, some of that ozone was being depleted. And so you can see here are higher levels, here are lower levels. We had a whole lot more ozone a long time ago. We're losing some of that ozone here. So we definitely had a decrease in ozone levels over these last 40, 50 years or so. Interestingly, a bunch of us developed nations got together and said we probably shouldn't destroy the ozone because too much UV radiation getting to the surface of the Earth means an increase in skin cancer for people, and that's bad. So we made some agreements in this thing called the Montreal Protocol and decided that we would reduce the amounts of CFCs that we were producing. And what's kind of amazing is we did reduce the amounts of CFCs that those developed nations were releasing. Ozone is actually, and I know it's kind of hard to see, but ozone it's better than it was. We're pushing more toward this way, less toward that way. So we are actually starting to resolve some of the hole in the ozone layer problems because we got together as a global community and decided that it was important. Might be time for us to do the same for climate change. And on that note, my friends, we have accomplished our video lecture. Oh, my slide got stuck. And objectives met. Concentrations of gases on the atmosphere have significant effects on climate. We know that. We talked about greenhouse effect. We have that short wavelength coming from the sun being converted into long wavelength radiation that gets trapped by those greenhouse gases. Carbon dioxide is the most significant of our greenhouse gases. We talked about electromagnetic spectrum, that short wave, that long wave. We compared and contrast methane and water. Water is super cool because it's polar. We talked about CO2 levels are increasing which is going to enhance the greenhouse effect. And then we did that quick little look, climate change and ozone depletion, both important. We're making some progress. We're not making progress. But I believe in your generation, my friends, you've got this.